Forces in general, right? What is a force? Can anyone give me like a broad definition of a force?
Is it related to like Star Wars?
Not quite. Yeah, push or a pull. Perfect. That's the textbook definition. A push or a pull exerted on an object. Push or a pull exerted on an object. All forces are going to be labeled with a capital F, and then they'll be followed with a subscript that is more descriptive. So we might have F sub G, which would be the force due to gravity, or F sub T, which could be a tension force. So all of forces are given with a capital F, and then they'll have a subscript that is more descriptive. But capital F is an abbreviation for force. So when you have forces, how does a force affect the motion? What are different ways that forces can affect the motion of the object that it's acting on? How can forces manipulate motion? Yeah.
Slow it down.
It can slow it down. Good. What else can it do?
Speed it up.
Speed it up. Okay. Forces can both speed up or slow down object. What else could it do? Okay. Could bring it to a stop all the way. Okay.
Could it like change its position?
Change its position or change its direction. Good. All those are good examples of what forces can do. They can speed up, slow down, or change direction of an object. Speed up, slow down, or change direction. So it's any sort of a push or pull. Okay, these are two vocabulary words that you might want to be familiar with. The system is the object that's being manipulated or the object that's having the force applied to it. The agent is the thing or the person or whatever that is applying the force. Okay, so the agent is the cause of the force. The system is the thing that's being manipulated or that's getting the force applied to it. Okay, so contact forces are anything that come in contact with it. Field force is any type of force that does not have to come in contact with the object. So gravity is a good example. But these are forces exerted without coming in contact with our system. Okay, gravity is acting whether or not an object is being touched or not, right? If something's free falling through the air, gravity is the only force, right? So if we drop something, we have gravitational force. We also might have a force that opposes gravity. Can anyone think of what that might be? As something's free falling through the air, gravity's pulling it down. What do you think might be trying to slow it down? Air resistance, right? That's another example of a field force. Okay, even though air resistance kind of has to come in contact with our object, that one's a little stickier, but gravitational force is a big type of field force. Can you think of any other field force? One of them is really big that we don't deal with a whole lot here, but you might be able to think about what it is. Yeah, magnetic force. Okay, we don't deal with magnetic forces in this chapter at all, but magnetic forces are a good one, right? You don't have to be touching something for it to attract that magnet. Okay, anything else? Okay, I don't need to talk about that. Okay, I have this table for you, and I printed it out, and I only have a few things I want you to fill in. But these are some examples of some of the most important forces we'll talk about. Okay, would you guys read this? And just, can you pass it out? Okay, so there's types of forces here, and you can see in this first column, there's a subscript that follows force. Capital F and then a subscript. Okay? These are important subscripts. They tell you what type of force they are. So I highlighted I crossed out some of the important things that I want you to write down and process, but you can copy them off of this table. If you need to move up a little bit, you can. Friction is a big one, normal is a big one, tension, and weight. So 1, 2, 3, and 4 are 4 of our big ones that we'll deal with a lot. be right back.
Jake, are you a degree?
No, not yet.
Okay, so this, for force due to gravity, you should see F sub G. Okay, that's really important. F sub G. Tension is Ft. We don't use thrust very often, so you won't need to know that. Spring, you don't use that often either. This is a normal force, and this is the frictional force. Okay, these two are really big, normal and gravitational. Friction we'll use pretty often. And we'll talk about one more. The other type of force that I use often is just called force applied, FAPP. And you don't need to necessarily have that in your table or anything. An applied force is anything that I push or a pull on an object. So if it says I push a box, you could put force push, force pull, whatever. I just put applied force. Now that we know the different types of forces, we're going to start drawing diagrams, and these are called free body diagrams. And yours don't need to be near this intense, right? This comes from your textbook. But what free body diagrams do is allow us to make a model of the system. Okay? And so when we make a model of the system, we're going to choose our system. You can draw out the book, and like here's what's happening in the system, right? It looks like the hand is pushing the book, right? Would you agree with that? Okay. You don't have to draw the book. The system itself can just be a dot, okay? Because that's as artistic as physics people need to be, right? As a dot, okay? So the dot represents the book. We're going to draw our forces as vectors in the direction of that motion. So vectors have to be drawn as an arrow. Good, they draw them as an arrow. That's okay. And they usually have to be drawn to scale, right? A proportional scale. So in this system and in this diagram, they go into a lot more detailed naming than I think they should, naming their forces. Okay? If I look at my object and I say this force is pulling it straight down and it's called the force of the Earth's mass on the book, what else do you think we should call that? What should be a better name for that?
Gravity?
Yeah, force due to gravity. Okay, so I don't need you to worry about these long naming on our forces, right? That's ridiculous. What's the force that pushes up on our object from the surface? That's on your table. No. Normal force. The normal force is exerted by any surface upward on our object. So any surface, anytime our object is sitting on a surface, there is a normal force that is being applied, and it's always perpendicular to the surface. So anytime our surface is flat, guess what? Perpendicular means straight up. Okay? So it's perpendicular to the surface, and it happens anytime our object is sitting on a surface. It means gravity's pulling it down, the object or the table or whatever surface it's sitting on is pushing it back up, okay, to hold it upright. The last thing they said was a force of hand on the book. We're just going to call that our applied force, okay? So our applied force. If there was friction, what way would it go?
The opposite of the location. Would go down.
Good. The opposite of our applied force. So if we had friction, it would go this way, right? It opposes our motion. So here we're pushing the book to the right. Friction would oppose our motion. They didn't say anything about friction, so we don't have to include it. But that's what a free body diagram is we're showing everywhere that a force is being applied to that object, right? Gravity, the normal force, and an applied force. Okay. We do have to make sure that we label each force with Fg, Fn, whatever it is, okay? And remember, our force vectors should be drawn to scale. And that doesn't mean we get out a ruler and we draw them to scale, but we do draw them to a proportionate scale. So I'll talk about what that looks like here in just a second. Okay. Okay, you don't see gravity like this. Our gravity vector doesn't look like this, Fg, right? It's not going into the object. They start at the object and they go away from. Okay, so we don't want it to look like that. Okay. We're going to do some practice with free body diagrams here a little bit at the end of class. Okay, so we'll do some as we walk through our problems, but that's all I want to introduce you to free body diagrams. And then we're going to move into something else, okay? So we will do some more practice with free body diagrams. You're going to need a diagram with like every force problem that you do, so you're going to get practice, okay? Next, we're going to look at something called the net force. What's it mean to have net of anything? Kind of.
It's like the extra.
No,
Accumulate
kind
above
of.
or insufficient.
It's like the profit.
Okay, yeah, you know of such thing as net profit. How do you calculate net profit? Or net income? Your positives minus negatives, that's it. Okay, good. So net means overall. Positives minus negatives. It's the sum of all forces acting on our object. It's our positive forces minus our negative forces. That gives us the net. So when you have a net income, that means it's what someone paid you minus what the government took out. That's your net income, right? Your income minus your outgo, that's your net, okay? So the same thing applies with net forces. Okay, the sum of all forces that acts on an object, that's your net. Positives minus negatives, okay? If an object is at equilibrium, an object is to be considered at equilibrium when our forces cancel out, which means it's at rest or it's moving at constant velocity. So I'm going to show you what that looks like here in a second, okay? Okay. Net force, if an object is at equilibrium, our forces cancel each other out, okay, which means our F net is equal to 0 when an object is at rest or when it's moving at constant velocity. That's important. So you might want to put that. F net equals 0 when it's at rest or when it's at constant velocity. Okay, and I'm going to show you how we get to that point mathematically too, but those are just conceptually two things that you might want to like put away here. Okay? F net is equal to 0 when our object is at rest and when it's moving at constant velocity. Okay? So let's look at how do we calculate net force based on a free body diagram. Okay? So you can think about net force in a little bit as kind of like a tug of war like scenario, right? If I've got an object here, I have an object here that has an applied force of 100 newtons left and an applied force of 100 newtons to the right. The result or the net of that would be 0. If I'm looking at my net force, I'm going to take my positive forces, which are always to the right, minus my negative forces, which are to the left. Okay, that's important. Positive is to the right, negative is to the left. It's just like we have direction in our previous chapters. Okay, so in this example, when I go to set up my net force equation, which you'll hear a lot, I would say F net equals F1 minus F2. Okay, why did I say F1 minus F2? F1 is the positive force, it's going to the right. And F2 is my negative force, it's going to the left. Okay, that's why I did F1 minus F2. So if I put my numbers in there, 100 minus 100 gives me a net force of 0. Okay, I know this is a lot more math than we can just see it right here, but we have to understand the process of this net force equation. Okay? Does that part make sense? The second thing I want you to remember about a net force equation, which is this guy right here, positive forces minus negative forces equal F net, is that we never mix horizontal and vertical forces in the same equation. Okay, we never mix horizontal and vertical forces in the same equation. Okay, so let's think about the next one. F1 goes to the right 100 newtons, F2 goes to the right 100 newtons. So if I set up my net force equation, I would say F1, would I add F2 or subtract it? Add, because they're both positive. So I'd say F1 plus F2, which means my net force would be 100 plus 100, which equals 200 newtons. Right? If I drew that scenario in a free body diagram, it would look like this. F1, F2. You can just draw them one right tail to tip next to the other one. Okay?
If they're going to the left, would it be negative 200?
It'd be like 0 minus 100 minus 100. So negative 200. This says 100 plus 100. Sorry. Okay. Yeah, Gary.
So the force that goes to the right are always positive?
Exactly. Forces that go to the right, we always consider to be positive. Okay? So last one, my net force equation here would be 100, then what? Minus 200, right? Because my 100 Newton force is my positive, my 200 Newton force is my negative. So it means my F net equals negative 100 newtons. Okay, I should have told you before the N at the end, it stands for newtons. That's our unit for forces. So you might want to put that in your notes also. Okay, the unit for force is newtons. And it's a capital N. So N equals newtons. That's the unit for all forces. So if it's measured with the capital N, that means it's a force. Okay, good. When finding the net force of free body diagrams, we take the up forces minus the down forces, which we didn't have any here, or the right forces minus left. So we always take positives minus negatives. That's really, really, really important. Net force is positives minus negatives. Okay? But we got to draw the diagram first. So here our forces were already drawn kind of in a free body diagram for us. And in all of our problems, that might not be the case.
Can you go back to
Yeah. All right, so the first thing we do is draw our dot, right? What force do we know is always acting? Gravity. And since it's on a surface, what do we know about another force? Okay, not necessarily. Okay, it does tell us to include friction, but what do I know is happening purely because it's resting on a surface? The normal force. Okay, so normal force and gravitational force, they happen for almost every object has those two. Any object that's on a surface has normal. What do I know about those two forces in terms of their size relative to each other? They're equal. How do you know they're equal?
Does the object stay, it doesn't move up or down?
Perfect. It doesn't move. It's not accelerating vertically. Right? We said the net force equals 0 when our object is at rest. And this object is at rest vertically. Right? It's not moving vertically. So our up forces have to equal our down forces. So I put the little congruent lines on there. You don't have to. If that makes you really understand, like, hey, these two are equal to each other, then put them on there. I'm not going to count you off for them not having, or they're not being there. Okay? Now it says it's accelerating to the right. So I have an applied force, right? Or a force push, or a force, it doesn't tell us if it's a pull or a push. But I have an applied force. So which direction does that need to go?
right.
To the right. Okay, so I say force applied. And then what do I know about my frictional force? Because it tells us to include friction. It needs to go opposite. It needs to go to the left. So does it need to be the same size as the applied force? Less than or greater than? Less than. How do I know it needs to be less than? Okay, good. It's not only moving to the right, it's accelerating to the right. Okay, so let's, I'm not going to go a whole lot further than that right now, but if it was moving at constant velocity, we would want these two forces to be equal, right? If it wasn't moving, then friction would be greater than my applied force, right? If I'm not applying enough force to get it started, that means friction is overcoming that, right? Friction is too powerful. But I'm moving my book fast enough, I'm applying enough force to overcome friction and make it speed up, which means my applied force is greater than friction. Okay? If those two forces were equal, that would mean my object was at rest, or it was moving at constant velocity. That's really important. Okay? Sec 1, the book is sliding to the left on a table. Ignore friction. What should be the only thing that changes here?
No friction.
I'm going to put this in there. So I want you to try this one on your own. At constant velocity. So a book is sliding to the left at constant velocity. All right, hold on. I'm saying two things that don't make sense. Never mind. Not constant velocity. Because it told me to ignore friction. I thought it said include friction. Okay, ignore friction. So that means our free body diagram should have a total of how many forces?
3.
3, good. April, give me one of our forces. Gravity. And give me another of our forces, Levi. Yeah.
Applied,
Okay, and which way is it going?
the left.
Left. Does it matter the size of it at this point? No. Okay, Jake, what's the last one?
Normal force.
Normal. Okay, and what's its size proportional?
It equals to gravity.
Good. Equal to the force due to gravity. Okay, the applied force doesn't have to be relative to anything because there's nothing that's opposing it. It said ignore friction. Okay, if I had said at constant velocity, you would have had to include friction because those forces would have had to cancel out, right? I can't say at constant velocity and then not include friction, so I was saying two counterintuitive things there. But ignored friction means it's going to be accelerating to the left. We've only got one force. The stone is falling at constant velocity. Include air resistance. Okay? A rock is falling. A stone is falling at constant velocity. So let's think about the one force that always acts. What is it? Gravity, Fg. Okay? Is anything moving it right or left? No. Does it have a normal force?
No.
No. Why not?
Because it's falling.
Yeah, it's not on the surface. But it says to include air resistance. So as something's falling to the air, what way is air resistance going? Up, right? Air resistance is opposing our motion. The last thing we need to say is that it's constant velocity. So what does that mean about those two forces? They need to be equal.
Would it be weight?
This is the same as weight. Fg is weight.
Wait, what did you write?
Is it F air?
I just put F air, yeah.
On the table, is that say F or little F or what is that?
No, it's not on the table. Air resistance is not on that table I gave you. So we'll have more than just the ones on the table, but those are the main ones.
So the air doesn't have a friction.
It's a form of friction, but usually friction has to have interaction of two surfaces. So they're both forces that can oppose motion, but no, it's not a type of friction. Good question.
So I'm just confused because I thought like since it's falling, the gravity would like overcome. So I thought like.
So at this point, in order to have reached constant velocity, it will have had to reach something called terminal velocity, which means it's reached a point in which its air resistance force equals its gravitational force. So it's still falling, it's just not speeding up as it falls anymore. Okay? Like if I drop a piece of paper, right, it's not really speeding up as it falls to the ground, kind of does that back and forth effect. That means it reaches its terminal velocity really quickly. So, if it says constant velocity, that means our forces have to cancel each other out. Right? Upward has to equal downward. Okay. Newton has how many laws? 3. So we're going to go over 1 and 2 today. First law says an object at rest will remain at rest. An object that's moving will continue to move unless something else acts on it. Okay? Or as long as that net force is 0. Newton's first law. This is also nicknamed the law of inertia. His second law has an equation attached to it. You don't need to have the big necessarily definition of it, but I do want you to have the equation. F net equals mass times acceleration. That's Newton's second law. You don't have to have the word version of it, but you've got to have the equation. Net force equals mass times acceleration. Mass times acceleration. Okay? Acceleration of an object is equal to the sum of the forces, that's the net, divided by the mass. So have the actual law, and then we rearrange it to say this. Okay? So net force, which we just worked on a little bit ago, can also be equal to mass times acceleration. So we're going to do some substitution in this chapter, substituting our equations. Okay? What do you think mass needs to be measured in? What do the units for mass need to be?
Grams.
Nope.
Grams.
Kilograms. Kilograms. What do you think acceleration needs to be measured in? No.
Meters, fine,
Centimeters?
meters squared.
Embedded.
Meters per second squared. Okay. So a Newton, which is a measure of force, 1 Newton is kilograms times meters per second squared, right? That's what the unit for force is. But we've now, I kind of, I don't know what you can even say, abbreviated it down to call it a Newton. Okay.
Meters per, 1 Newton equals kilograms times kilograms per second.
Kilograms times meters over second squared. That's what a Newton is. I'm going to give you that on the next slide, I think, but I just got ahead of myself. Okay? So units for force are newtons. All right, we already said that, so we're good. Okay. Now we're going to start doing the math that goes with it. So estimate the net force needed to accelerate a 1,000 kilogram car at 4.9 meters per second squared. We don't really need the free body diagram yet. We're just looking at the net force, and we're doing the math that goes with it. So we're going to eventually start putting all of that together, but we're doing introductory stuff first. So F net equals MA. Okay, so this problem is really as easy as it seems. 1,000 kilograms times 4.9. That's it, right? 4,900 newtons. What'd you say? What net force is required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour within a distance of 55 meters?
So we have to find acceleration with the kinematics equations. What is that?
Yeah, your kinematics aren't going away, sorry.
Oh my god. She really just did that.
It's not me. Lane Newton.
Yeah, no harm in the messenger.
Yeah.
Yeah.
All right. A couple different things here. We have our mass, which is good. We need that. Mass is 1,500. We said our velocity initial is 100 kilometers per hour, which won't do us a whole lot of good. Our distance final is 55. And what is our velocity final? 0. Okay, so we have to solve for acceleration first. We cannot solve for, we can't solve for net force without acceleration. And we have to solve for acceleration first using our kinematics equation. Okay, so if you don't have your equation sheet out, you might want to grab that.
Did you say that?
So we can use, so can
Oh, I wrote the wrong thing, yeah.
Can velocity be in kilometers?
We have to convert that to meters per second. Remember the shortcut to go from kilometers per hour to meters per second?
Divided by 3.6.
We divide by
If Jake's learned anything, it's
3.6.
I swear to you. It's one thing I'll take away from this class. Just divide everything by 3.6. Eventually you get 1.
That's your answer. It's just 3.6.
Okay, so we have about 416, 417. Is that what you got? To go from kilometers per hour to meters per second, we divide by 3.6. That's the shortcut, from kilometers per hour to meters per second, because we can't have our velocity in kilometers per hour. So now I need to solve for acceleration.
I got 27.878. Something is either wrong with my calculator.
1,500 divided by 3.6?
100.
What?
Oh, I did the wrong, I wrote it on the wrong line, sorry.
I was like, hold on, wait a minute.
I didn't question it, I just wrote it down.
No,
I know, I just went with it and I typed it. I was like, wait.
sorry, you should question it. I took my math. I don't know why. Sorry. All right. Tell me what you got.
27.78.
That seems better. All right. Sorry about that. You guys looked at me funny, but no one. All right. Here we go. I make mistakes. I'm not perfect. Okay. So 27.
I didn't even punch it in.
Okay. What kinematics equation should I use?
I don't know.
Third one.
Yeah,
The third one, right? I can't use the. I don't have time, so I have to use the third one. So to find acceleration, right? I'm gonna go 0 squared equals 27.78 squared plus 2 times a, which is what we're solving for, times 55. You got to use kinematics to solve for your acceleration of your object. What was the rate at which this car slowed down?
Sheesh.
Yeah, you don't have time, which is why we use the third kinematics. Okay, I got about -7.
7.02, yeah.
Does that seem about right? Better than when I did it at the wrong problem? Okay, so that means when I solve for F net, I'm taking mass times A and get my net force.
Why did I get 380?
That's damn right.
Music,
2005. Wait, is it?
Because it says the force that's causing it to come to a stop has to be opposing the motion. So if the car's moving forward, there must be a negative force, whether it's the brake, whether it's friction, whether it's both. It didn't really ask us for what type of force it was, right? But we know that the forces that cause this car to come to a stop were in the negative direction. Okay?
Do we have to draw diagrams for these?
No, we're not quite to the diagram part of it. Eventually we're gonna combine both these free body diagrams and our net force equation. All right, so let's see what we need here. It says a 2,000 kilogram car has an acceleration of 3.12 to the right. If 300 newtons of friction is acting, what force is being applied by the car? So we've got to apply some force to the car to get it to move forward, right? Whether that's hitting the gas pedal, right? That's applying a force. The engine is moving the car forward. Okay? So if I set up my net force equation, okay, I can start with a diagram. Okay, let's just set up my diagram first. What forces do I always have acting? Gravity and... Is my car floating in the air? No, it's on the surface, so it means normal. Okay, I've got a normal force too. Now we know the car itself is applying a force to the right because it says we have an acceleration of 3.12. Okay, to the right. So that means the car is applying some force. So you can put force of the car, you can put force applied. I don't care what you name that force, right? I almost always just use applied because it's kind of a blanket statement. Then it tells us that we have a force of 300 newtons being applied in the form of friction. Okay, do we see where we're getting that diagram from? Okay. We know that the car is applying some force, and that's what we are being asked to solve for. What is the applied force on the car? Right? That's what the question is asking us. Okay? So as we go to set up our net force equation, we would say F net equals force applied, because that's our positive force, minus friction, which is our negative force. This step right here, that drawing that diagram and getting to this part of our problem, is like the most important step for every problem going forward. If you can get that part of it down, you're going to be really successful. Getting your forces plugged into your net force equation correctly is really crucial. Okay? You notice that I didn't put in gravity in the normal force, right? Because my car's only moving horizontally. It's only accelerating horizontally. That's the forces that we are concerned with. We don't ever put vertical and horizontal forces in the same equation. Never. Okay?
Make it with the gravity. If we know it's a car and it's showing just horizontal.
Because without those forces, your diagram is incomplete. So although they're not affecting our math now, eventually they will for more complex problems. Okay, so you just get used to drawing them. Okay? All right, now we can start putting in our numbers. What do we know that the F net is also equal to? Good. We know it's positive forces minus negative, but we also know that F net is equal to mass times acceleration. So I'm doing like a substitution right there. Right? If we know that F net is equal to mass times acceleration, I'm just plugging in MA for F net. Does that part make sense? Okay, I know my applied force is what I'm solving for, and I know that friction is 300. Okay, I also know my mass and my acceleration values, so I'm going to plug in 2,000 times A. Is my acceleration positive or negative? Positive. If it would say to the left there, right, we'd have to make it a negative 3.12. So just something to think about. But it says it's to the right, so that's positive. Equals force applied, which is what we're solving for, minus 300. Okay, now we can do the math to solve for that applied force. Okay, I solved this by multiplying, and then I added over my 300 to get my applied force by itself. Okay, since it was minus 300 originally, I added it over to get applied force by itself. Okay, so setting up the diagram and getting to this net force equation is really, really, really important. Okay? What other questions do we have? Okay. Knowing what we know so far about Newton's second law and about drawing free body diagrams, what's the net force of an object that's moving at constant speed? 0, right? It's 0. So let's look at why that is the case, right? We talked about how if it's at 0, our forces have to equal each other, right? So let's say my frictional force and my applied force are congruent. Okay, that means my net force is 0. But if I'm moving at constant velocity, what's that have to do with my acceleration? What's my acceleration have to equal if I'm moving at constant speed or constant velocity? 0. Right? If I'm moving at constant velocity, I'm not speeding up or slowing down. So my acceleration is 0. Then, when I plug it into F net equals m times A, and A is 0, that's another way for me to prove my net force is 0. Okay, so constant velocity means a net force of 0. Okay, which is how you know those two forces should be congruent. Let's try this one. Force of Sam, and then force of Andy. Right? There's some object in the middle. We don't really know what it is. We can assume it's sitting on the ground, in which case the normal force and the gravitational force would be equal to each other. Agree with that part? That's not affecting our problem. So again, it's helpful to draw it so you have a complete diagram, but it's not going to mess you up if you don't. Okay, they begin pulling in opposite direction. If Sam pulls with a force of 16 newtons, and the rope accelerates away from him at 1.75, with what force is Andy pulling? So that means we are solving for FA. Would you agree with that part? That's overall what we're solving for, is his force. So I've drawn my diagram. I'm going to set up my net force equation, positives minus negatives, so force of Sam minus force of Andy. Okay, and then I can start plugging in my numbers. Okay, I know Sam pulls with what force? 16. And I know I'm solving for force of Andy, so I'm going to leave that as the variable, right? What do I know I can substitute for F net? Mass times acceleration. So mass we know is 0.75. And then what do we know about the acceleration? It is? It's negative 1.75. Because we chose Sam to be pulling positive, and because it says it's accelerating away from him, acceleration is negative 1.75. Okay, so if I do the math that goes with that, then we just take the negatives away. So we'd say Andy pulls with a force of 17.3 newtons to the left, right? You can either leave that negative to show that it's going to the left. It's not that big of a deal. But essentially, mathematically, did I do that right? Is that what we all got, or not so much? We multiplied these two together, and then we subtracted over that 16. Okay, and then I just canceled those negatives. So I said Andy applied a force of 17.3 newtons, and it would be to the left. Okay. Okay, so I set up F net equals 20 minus 15. M is 30 times A equals 20 minus 15, which is 5, so I'm dividing by 30. And I get A 1.167 meters per second squared.